So today we're gonna start a new series on statics, and this video is nothing more than an introduction of statics and what it's all about. So statics is nothing more than basically analyzing systems. In this case, it could be an object or multiple objects that interact somehow, but more specifically, statics is nothing more than objects that are stationary, which is what static means. So any stationary objects is what we're going to be learning to analyze the forces within that system. So the common object or structures that we analyze in statics usually have to do with beams. Usually in construction you see I-beams, but for now the geometry doesn't really matter. What matters are the concepts of analyzing the forces within the system. So right here, for example, we have a beam, and here we have two support points. So in this case we have a hinge, and on the other side we have a roller. Now when you guys we'll be going over the different, I guess you could say, the bases or the foundations that the beams are on. And depending what support you have, either a hinge or a roller, you have different what's called a reaction force. So just imagine here you have some force, in this case let's call it F. Now of course the ground is going to react to this force, and we have what's are known as reaction forces. In other words, the ground or the supports, whatever is holding up the beam, have to react with some force. In this case, let's call it F of reaction 1, the force of reaction 1, and the force of reaction 2. So for every action, there's an equal and opposite reaction, which essentially is the third Newton's third law, which is what we'll be utilizing for this. Now, when it comes to stationary objects, we know that there is no motion. So that means the sum of the forces along any direction is equal to zero because we have the mass of the system, but in this case there is no acceleration. So the summation of forces, you could say either along the x direction or along the y direction. You could use any coordinate system you like. So let's call this the y and let's call this the x coordinate. So the summation of forces of either along the x direction or along the y is equal to zero because the object is stationary. Now, another one that we utilize often is the summation of moments along any point. In this case, let's call it point O. And for this diagram that we have here, let's just assume this is point O. Now, the summation of moments, in other words, the summation of torques and moments are essentially the same thing here. So the summation of moments along with respect to the O here is equal to 0 in this case, and we could use counterclockwise as our positive direction. And for the X or Y, you could either use this as the as your positive, up as your positive as well. As long as the signing conventions are consistent, you could use whatever convention you want. Now to explain a little bit more about the summation of moments equal to zero is the summation of torques. If there isn't any torques acted upon the system, that means this system that we're analyzing, whatever it may be, does not rotate along this point O. And of course, since it's stationary, we know this is true. So these are the ones that we use, the summation of forces along either X or Y, as well as the summation of moments about with respect to any point is equal to zero. And these are the main ones you'll be utilizing to finding unknown forces in these kinds of systems. Now, the reason these concepts are so important is because once you know the reaction forces as well as how those forces are acted upon different beams, like let's say for instance this configuration. Now, all these lines I just drew right here are essentially just beams, and these are the supports. We have another hinge here, and we have a roller, which I'll get into the supports in a bit. Now, for instance, in this kind of structure, knowing the external forces that are acted upon it, it could also be distributed loads, right? It could be force per every so many feet that's exerted upon a uniform distributed load, as it's otherwise called. Once we know, if we know the external forces and we're able to solve for the reactionary forces, here and here, we're essentially able to determine at every single point where these beams interconnect, we're able to determine all the forces along every single beam. And this would be useful once we get into stress analysis, which will be in strengths and of materials class. But for now, we're learning the fundamental concepts to analyze forces in these kinds of systems. So now let's get familiar with what's known as supports and how their reaction force is applied. Now supports is just as simple as it is. It's nothing more than what's supporting the beams in the structures. So for instance, we have. So now let's take a closer look at one of the supports. This one is known as a hinge. It also has what's called a pin here. So this is one of the supports that we have. And essentially, if you can imagine a side view of this, essentially it's the beam going in between two plates. Let me go ahead and draw that. Now, as a side view, we're looking at the cross section of this beam right here. And this is what's known as the hinge here. Now, right here, there is a pin that goes right through the hinge, through the beam, that essentially is how it supports that structure. And when it comes to this kind of support, you always have two reactionary forces. You have one along the y direction. Let's just call this a force along y. And you have a force along the x direction as well, F x. So the hinge always has two reactionary forces. You have the force along the x and along the y. Now, this does not necessarily mean there will be a force along the x or along the y. This is where you're going to apply the summation of forces is equal to 0 and solve for any unknowns in a particular system. So this is the support of the hinge. Now let's go ahead and do the roller. So here we have the structural beam, then we have a roller. It could be a cylindrical roller. And essentially this, of course, here is the ground. This is how I symbolize the ground here. And for this, the reactionary forces for a roller is nothing more than a reaction force along the y direction only. This support is a roller, and the reactionary force is only along the y direction. There is no force along the x direction because, just as the name suggests, it will roll if there's any force along the x direction until it's stationary, and therefore it's not going to have any force along the x. That's the common use for a roller. When it comes to any thermal expansions of a structure, the roller will roll along as the structure expands or contracts. And so this only has a reactionary force along the y. And these are the two common supports will be seeing for the problems that we'll be doing here. Now, when it comes to the fundamentals of analyzing the forces for systems, it's not only for beams and for structural beams. It could be used in anything. It could be used for a system that may have a spring. It could be used for pulley systems, and so forth. These fundamental concepts can be utilized in more than just structural beams. So just to do a quick example here, as a warm-up, I guess you could call it. We have this structural beam. One of the supports is a hinge, the other one is a roller, and we have a force applied here. We call it F1. We have an external force applied right at the center. So we have from here to here, here to here. Let's call it this one L2, length 1, and length 2. So now our job is to find, with this external force applied to a system, what reaction will our supports have? What are these reactionary forces? Let's call this F of R1. Let's call this one F of R2. This one F of R1. Well, now this one may be a little bit confusing because I'm using nothing more than variables to represent the forces and the dimensions. But once we get into doing problems, it'll be a lot easier because we're going to have actual numbers. So now we're going to define our coordinate system. Of course, this direction is going to be our y, and this is going to be our x. Oh, one thing that I forgot, the hinge also has a reactionary force in the x direction. So let's call this one FR1x, I guess. But of course, once we remember, it doesn't necessarily mean there'll be a reaction of force along the x, but when it comes to a hinge, it may be possible. So here, let's go ahead and do along the x direction because it's going to be the simplest. So the summation of forces, since this system is stationary, it's not moving, there's no acceleration. So the summation of forces, in this case, let's do along the x direction, is equal to 0. So now let's defined what direction is positive. I'm going to say going to the right is going to be positive. So now analyzing this system, we have only the reactionary force R1x along the x direction. This reactionary force R1 is along the y, so we don't include it. This one is along the y direction as well, and F1 is along the y direction. So the only force here is the reactionary force R1 of x, and this is equal to 0. So for this hinge, in this specific instance, there is no reactionary force along the x direction for the hinge. So this one you could just cross out. Now let's go ahead and do the summation of forces along the y direction is equal to 0. And let's say up is positive in this case. So we have the F of the reactionary force 1 is in the positive direction, so it's positive. So we have the plus the second reactionary force F of R2. It's also positive because it's upward. In this case, F1 is going downward, so it's negative. So take away F1, and this is all equal to 0. So we have FR1 plus FR2 take away F1 is equal to 0. Now we have here two unknowns. Our reactionary force says here, both of them are unknown. The only known is F1 here. So this is where the summation of moments comes into play. So the summation of moments along any reference point you would like to use. I'm going to use O, and I'm going to designate where this hinge is located as point O. So the summation of moments at that point with respect to that point O is equal to 0 because there is no rotation in this system. So we know that. And we'll say counterclockwise direction is positive. So when it comes to moments or torques is always going to be the force times the perpendicular length with respect to whatever point. In this case, we decided to go with O. So F, the reactionary force FR1 times, in this case, is going directly at that origin. So in this case, there is no perpendicular length, so it's going to cancel out. It's going to be 0. There is no moments about this point 0 that would cause any kind of rotation. So in this case, there is no moments caused by this reactionary force. So now FR2 here, if it were to go, if this were to push up, then it would cause a rotation along this point in the counterclockwise directions. So you see that it would move it up this way. So this would be positive, the reactionary force 2 times your perpendicular length would be L1 plus L2 for your torque. And then we have F1, which would have the opposite effect. It would rotate a lot with respect to that point O this way. It will rotate it clockwise. So in this case, it's going to be negative F1 times your perpendicular length. In this case, it's L1 is equal to 0. So now we're able to solve for F of R2. So we bring basically F1, L1 to the other side of the equation, so now it becomes positive, and then you divide both sides of the equation by L1 plus L2. So you have the reactionary force at 2 is equal to F1 times L1 divided by L1 plus L2. So now that we have the reactionary force R2, we could go ahead and plug it in this equation, and our only unknown at that point would be the reactionary force at 1. So once you basically just move some stuff around, you have FR1 is equal to move F1 to the other side, take away FR2. And this essentially is what you saw for the reactionary forces FR1 and FR2. Now, right now, it's kind of confusing because of all the variables, but once we get into the doing numbers, it'll be a lot easier. And so this is the introduction to statics, nothing more than analyzing the forces in stationary objects. And that's all it is to it. Now, if you feel overwhelmed or a bit uneasy because you see a lot of variables here, don't worry. Little by little, you'll start getting the hang of it. You'll be doing simple problems with numbers instead of seeing all these variables, which could get kind of messy here. But little by little, you'll start to learn these basic concepts.